audible to everybody? All right. Good morning. My name is Mathew, and my paper is titled Lifetime of Oil Paper at under pulse stresses at different frequencies. These results were done from my master thesis and supervised by Professor Muhammad at NTNU. A summary of today's presentation. It might take a bit over 10 minutes, and we'll have a couple of minutes for questions. I'll start with an introduction. I'll talk about the test setup that I used, finally the aging experiments that we conducted, and then finally ending with some conclusions. If you lose track of the presentation, I'll keep this at the bottom, and the slide number is on the top right for your questions. I'll start off with the introduction. So, well, we talked a lot about power systems in this conference and how we have an increasing number of powertronic interfaces that are coming up in the grid. And a major enabling factor of this transition is wide bandgap semiconductors like silicon carbide. One important powertronic interface is the solid-state transformer. Now, the solid-state transformer has a medium frequency transformer. It was patented back in 1970. The idea is that the higher frequency allows smaller volumes and therefore higher energy densities. Also, the increasing amount of powertronics gives us more control over power flow. But the consequence of this is that the insulations in these medium frequency transformers will experience a lot of different kinds of stresses, which have never been studied before. So, and these stresses are characterized by a lot of different parameters, but the main important parameters are these two: the peak voltage and the switching frequency, which are known to degrade insulation lifetime. So my master thesis was quite simple, and in that case, the first idea was to develop a pulse modulator that can produce these kind of pulses across capacitive samples. This has not been done before. The second half was to obviously investigate the performance of oil paper under these pulse stresses. The paper we submitted for this conference, however, is only about the second one, so I will try to focus more on that. Quickly talking about the test setup. Well, the pulse modulator looked something like this. So we start with rectifying the grid supply. We then charge the DC link. We had an edge bridge pulse generator to produce pulses. These pulses were stepped up by a pulse transformer of a very high turns ratio. It was 1:50 in our case. These pulses were stepped up with the pulse transformer. These pulses were then conditioned with test elements, and before finally being applied across the insulation sample, which is a zero. After a lot of trial and error, failures, and issues with generating a pulse modulator, we finally arrived at something that looked like this. A small transformer. We have the high voltage winding over there, and to give you an idea, the primary winding was concentric, so we designed to be inside. It had 4 turns, and the secondary had 200. So what did the final pulse modulator look like? Well, we had the supply, we had the rectifier, just like before, we had the DC link and the pulse generator, we had the transformer, finally the test elements, and then the sample, and then a bunch of other measuring instruments. The final setup looked something like this. You can follow the red line. It goes from here, goes all the way around, gets stepped up by the transformer. This is the resistor bank. This is the high voltage capacitor, and finally we have the oil sample. And an oscilloscope here to see if you're finally, the output waveform, we had something like this. But then with the test elements, we were able to make it something pretty like this. Then we could control the frequency as well. At 50 kilohertz and at 10 kilohertz, we got the same rise times. So in the oscilloscope, we are seeing bipolar rise times because these are bipolar waveforms, bringing the unipolar rise times to just 1.84 microseconds. And this was a feat that was not accomplished before. let's move on to the interesting part, the aging experiments. We had samples that were impregnated in a vacuum oven, dried and kept under oil at all times. We had two kinds of electrodes, the conical electrode and the cylindrical electrode. These had to be dipped in oil to prevent surface discharges, obviously. Then we had to tune the sensitivity of the pulse modulator to make sure that it's breaking at the right moment. And if you didn't break it at the right moment, you would have these aggressive burn patterns. With these aggressive burn patterns, we also had to keep polishing the electrodes after every single test that we performed. The first test that we did was a ramp breakdown. We started at 1 kV peak per second. We took up the voltage at 50 kilohertz. And we saw what breakdowns we got with two different electrodes. We got something like this, which kind of makes sense. We see that the cylindrical electrode has, let's say, it breaks down at lower breakdown strengths because it applies a more uniform field across the sample as opposed to the conical electrode. And for this reason, we then select, these are some Weibull parameters, and for that reason, we selected the cylindrical electrode for the aging experiments. Moving on to the aging experiments, we performed 292 tests in total, which corresponds to about 10, 11 hours of testing time. We selected different electric field strengths, depending on the breakdown strengths that we performed before, and we got a graph like this. This is a bit messy graph, so maybe we clean it down like this, and this looks better. We see that the first thing that we see is these lifetime curve parameters. We see that 50 kilohertz, we have shorter lifetimes. So the higher frequency severely degrades lifetime of oil vapor insulation. The second thing which was interesting that we saw was this transition point. You see here in the 50 kilohertz line. Below a certain value of field, around 20.5, the slope of the Weibull lifetime plot drastically reduced. And then we started thinking about what could be the cause for this. Well, the first hypothesis was that maybe there could be some field enhancement at the edges that is causing this issue. But then we also observed that no breakdowns happened at the edges. They were all at dead center in the insulation samples. The next hypothesis that we had was that there are oil-filled cavities inside the insulation samples. And what happens is that when the E field exceeds the local partial discharge inception voltage of these cavities, it initiates partial discharges and then thereby shortening lifetime samples of oil. However, this needs to be verified, but this seems the most likely cause. Also, last interesting thing that we see is where exactly did this breakdown happen? So we had breakdowns during the fall time, the rise time, the positive pulse stop of the pulse, as well as the negative pulse stop. But the most common was during the fall time. Finally, I'd like to end with conclusions and let you all go for coffee. Three main conclusions. First, what is the effective frequency on the lifetime of oil vapor? Well, we noticed that an increase in frequency aggressively reduces lifetime. What is the reason for the observed transition point? Well, we hypothesized that it is because of oil-filled cavities, but it needs further verification. One possible way of doing this is having another lifeline at 30 kilohertz and seeing if that undergoes the same transition. And finally, lifetime testing at higher frequencies taught us a very important observation that if we increase the frequency, we can allow lifetime testing at much lower values of electric field. And yeah, so these are the three main conclusions, and if you have any questions, please feel free to ask me. Thank you.
Okay, it's nice to see the lab where the velocities is actually. Yeah. some couple of years ago. Questions? Yes, Howard.
I guess I usually ask questions from the point of total ignorance. So transformers are absolutely not my fuel. I'm just curious about the, I think you mentioned the rise time of the pulse was something like 1.4 microseconds.
Yes.
So how does that, because I know we have rotating machines, so therefore when we were looking at vertified drives, typically we're looking at rise times that are in the sort of like 0.1 microseconds. So therefore I'm trying to kind of like think in terms of why there's a slower rise time with respect to this application if you're still hooked up to an IGBT-based drive or worse, a silicon carbide-based drive.
Thank you for the really good
And
question.
thanks for the presentation, by the way. So.
Thank you. So two things. First thing, yes, these issues that we will face in solid-state transformers is very similar to what we faced in the 1990s with inverter fed drives. The difference, however, is when we talk about SSDs, we talk about different rise times and different frequencies, and that's the reason why we thought 2 microseconds is a good bet. The second reason is we just couldn't go lower. It's extremely difficult to give you an idea, to be able to like bring something down, like to be able to bring down the bandwidth of a pulse modulator is extremely difficult, and that's why it was the best that we could do, 1.84. But bringing back its relevance to solid-state transformers, with the literature review that I conducted, it is highly relevant. So yeah, we'll have to see where we go.
Thank you.
Yes,
maybe you can show again the slide with all the measurement results. Yeah, that one. Are you really sure that for the 50 kilohertz results we have a change of the lifetime exponent? It's always difficult to handle experimental results, and what kind of distribution do you apply? It's viable, it's normal, how you evaluate the haltant results and so on. Maybe it's only, again, one lifetime exponent.
Right. Yeah, okay. Thank you for the question. Yes, we do include, first of all, we do include the haunted experiments as well in the median. The reason for this is there is a chance that there can be insulations which have a breakdown somewhere, and we have to include them in the statistical distribution. About the possibility of this transition point even being that place, we need to populate this area and make sure that this point is actually where it is. But the problem is, if you see the amount of time it takes to perform these tests, it's in several hours. And that is another limitation. So with more time, we'll be able to populate these results and be able to actually ensure that this point is there. And the next thing, what I said is having another line at 30 kilohertz and seeing if it follows a similar transition point. But once we have those results, like you said, we'll be able to properly verify that this is actually what is happening. Thank you for the
okay. Klaus was first, but it's a very short time, and then we need a coffee break.
Oil paper insulation. I think, in my opinion, most of those devices for power electronics converters straight use electric insulation with air as a distribution.
Right. So two things. For the medium frequency transformer, they are usually not. They don't use solid or oil. Solid. They always use oil paper for the same reason that transformers, normal conventional transformers, also use oil paper. It's a very easy liquid, easy insulation to deal with. It's very forgiving, and also it allows us to continuously perform acid management. So that is why in a lot of literature it's said that oil paper is probably the way to go with medium frequency transformers.
Okay.
Yeah, thank you.
Okay. I think you only have 20 minutes on the break.
Yes.